Welcome back. In this lesson, we're going to move on to the hexadecimal number system. You should be able to represent positive numbers in hexadecimal notation. You should also understand how and why hexadecimal is used and why it is a beneficial method of data representation. You should be able to convert positive hexadecimal numbers to and from denary. A maximum of 4 hexadecimal digits will be required for the exam. You should also be able to convert positive hexadecimal integers to and from binary. A maximum of 16-bit binary numbers will be required. You should be able to represent numbers stored in registers and main memory as hexadecimal. And finally, you should be able to identify the current uses of hexadecimal numbers in computing, such as defining colors in HTML, media access control addresses, assembly languages, machine code, and debugging use. So let's start by looking at what hexadecimal actually is. Hexadecimal is a base 16 number system, which is used in computing. Base 16 means that each position in hexadecimal comprises of one of 16 options. Now our number system is base 10, so we have the digits 0 to 9. In hexadecimal, we've got these additional 6 digits. So we use A to represent 10, similarly B for 11, C, D, E, and F all the way to 15. The 16th option is quite clearly 0. We cannot use 1, 0 to represent 10 because 1 and 0 are already symbols that have been used in our number system to represent other numbers. So you can't just combine them like that. So you've got to come up with a unique symbol. So we use A for that. A, B, C, D, E, and F. Now on screen, you will see the symbols used for different number systems. For binary, it's just 0 and 1. Those are the 2 digits. For decimal, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For hexadecimal, we have 0, 1, 2, 3, 4, 5, 6, 7, and 9, A, B, C, D, E, and F. And A is 10, B is 11, and so on. For hexadecimal, as long as you can remember that A is 10, you can work out the rest of the values just by incrementing by 1. Okay, so why use hexadecimal? Why use another number system? Well, programmers often use hexadecimal when writing and analyzing computer programs because it's easy for a human to read hexadecimal rather than binary. Binary is quite complicated, takes up too much screen space. So large numbers can be represented using less positional spaces. Now, if you compare the binary base 2 number on screen for 255, that's just straight 8 ones. In decimal, it's 255. So we've got a bit of a benefit. We're using 3 spaces instead of 8. But in hexadecimal, it's F and F. So we're using 2 spaces. So the bigger the number system, the less symbols we use to represent large numbers. And that's quite useful when we're dealing with huge numbers in computer science. Okay, let's look at basic conversion, binary to hexadecimal. The algorithm's on screen. There's 4 key steps. From right to left, split the binary code into groups of 4. So we start from the right and we split them across in groups of 4. We write them separately. You write the correct base 2 headings above each of the bits. You then work out the decimal value for each group of binary code, and you change any of the decimal values that are above 9 into the corresponding hex symbol or hex code. So if you wanted to convert 11000111 into hexadecimal, we're first going to split it into 2 sets, and then we're going to write the place headings on top, which is 1, 2, 4, 8 for both of them. Then we're just simply going to add them together. So the first group on the left gives us 12, and since 12 is C in hex, we write C. The second group gives us 7, so we simply write 7. So the total hexadecimal representation is C7. Now, if you want to convert denary to hexadecimal, there are 2 ways you could do that. First is to divide the decimal number by 16, and we use the division method just like we did that for binary. We keep a note of the remainder, and it's generally between 0 and 15. So we keep repeating the steps until we reach 0. So for example, 242 divided by 16 gives us 15 remainder 2. We write 2 on the side. Then we take 15 and divide it by 16, which basically is 0, and the remainder is 15 because 16 doesn't go into 15 at all. So it's 0 remainder 15, and 15 is F. We then write it down from bottom up, F2. Now you could do this another way, which is to convert 242 into binary in the first place, if you find that easier, and then use the split 4-bit method. So we take the binary number, we go from right to left in groups of 4, we split them, and then we convert each group back into hexadecimal. As you can see on screen on the right hand side, 242 is 11110010. We split them into groups of 4, and 1111 is F, and 0010 is 2. So F2, which is the same as what we got from the first method. To convert hexadecimal to binary, it's even easier. First, we change any hexadecimal letters into their decimal equivalent. We then work out 4-bit binary code for each decimal value. So if you wanted to convert DA4 into binary, we write D is 13, A is 10, and 4 is 4. And then we convert 13 into 4-bit binary, which becomes 1101, 10 into 4-bit binary, which becomes 1010, and then 4 into 4-bit binary, which becomes 0100. Then we put all of them together. So DA4 becomes 1101, 1010, 0100. Converting hexadecimal to binary is pretty simple. To convert hexadecimal to denary numbers, we first write the correct base 16 headings above the hexadecimal values, and we start from right, which is 1, and each new heading is the previous multiplied by 16, since hex is base 16. We convert any letters A to F to their numerical values, and we multiply each value by the heading. We then add up the answers. So if we wanted to convert AA5 to denary, we would just simply write AA5. On top of 5, we'll write 1. On top of the first A, we'll write 16. And on top of the second A, we'll write 256, because 16 times 16 is 256. We then write AA5 underneath it, but since A is 10, we just simply write the value 10. Now 10 multiplied by 256 plus 10 multiplied by 16 plus 5 multiplied by 1, which gives you 2560 plus 160 plus 5, which then gives you a total of 2725. And 2725 is the denary equivalent of AA5. Of course, there's an alternate way here as well. You can convert AA5 into binary first and then use the binary headings to convert it back into denary. That's possible, but I find this method a lot more simpler. However, you can use any method that gets you to the answer. Okay, so what are the uses of hexadecimal? Well, we can use them for media access control addresses. A MAC address is a number which uniquely identifies your device on a network or the internet. The MAC address relates to the network interface card, which is inside a device, and it's normally written as D5-BE-E-9-8D-44-9C, something along the lines. You can normally find that in your network settings. Expressing MAC addresses in hexadecimal format makes them easier to read and work with. Other uses include assembly code, HTML colors, and memory dumps. Now, you don't really need to go into detail here, but HTML colors, there's 16.7 million possible colors. So if we try to use binary to represent them, that'll take forever. So therefore we use hexadecimal. Assembly code, again, the same thing. We work with large numbers. And memory dumps, when we get memory addresses output because a computer program's crashed, it's better to use hexadecimal rather than binary. Otherwise your screen will be filled with zeros and ones and they won't make much sense. So hexadecimals are beneficial over binary because they are easier and faster to work with for a programmer. They also take up less screen space, and it's easier to find mistakes and debug or trace a program when you're using hexadecimal rather than binary. Just remember that a big benefit of hexadecimals is that they're easy to convert to binary if needed, because each group of 4-bit binary can go straight into a hexadecimal digit. Now, in the examples above, all values are physically stored as binary in the end anyway, so you never save any storage space using hexadecimal. So never give that as a reason that you save storage space. You don't really save any storage space, it's just on-screen space. Never give storage space as an example of a benefit for hexadecimal. You will lose the mark. We can also represent numbers stored in registers and memory locations in hexadecimal. So on screen, you see a register with a number, and you have to convert that into a hexadecimal number. So it's pretty straightforward. We split it into 4, and we convert each 4-bit binary group into the relevant hexadecimal digit. So 1001 equates to 9, and 0111 equates to 7. So 97 is the hexadecimal equivalent of the binary number in the register above. You could get questions like these as well, so don't get stumped by them. They're basically just normal conversions. Okay, that's about it for this lesson. Hopefully you can answer the following questions. What base system is hexadecimal? You should be able to identify 3 uses of hexadecimal. You should be able to convert numbers like 1011, 1001, 1110 to hexadecimal. You should be able to convert 312 to hexadecimal, and similarly, you should be able to convert 2B to denary, or perhaps binary as well. And finally, you should be able to answer why we use hexadecimal, what are the benefits of storing numbers in hexadecimal. Remember, never give saving storage space as an answer. They just take up less screen space and make programs easier to debug. Those are the kind of answers we're looking for. That's all for this lesson. If you do have any questions, get back to me. Otherwise, I'll see you in the next one.